Okay, so in this workshop, workshop 4, the whole workshop is devoted to proving Bézout's lemma, or possibly Bézout's lemma. Don't know the correct pronunciation. Anyway, however you pronounce it, it's an important result, and we already used it when we were talking about the fundamental theorem of arithmetic. Now we're going to have some standing assumptions throughout this workshop, and I'm not going to keep mentioning them. So A and B are integers. We don't know what they are, but at least one of them is non-zero. That's so that you can take the highest common factor of them. So we won't ever say what A and B are, but they are both integers, and at least one of them is not zero. And we'll just use A and B throughout this workshop, okay? D is going to be the highest common factor, the HCF of A and B. And that's not going to change at any point in this workshop. So they're going to be constants throughout the whole session. We don't know what they are, but they are, all three of them are integers. D is going to be a positive integer. It's the highest common factor, so it could be 1. If A and B don't have any common factors except for 1, any positive common factors except for 1, then D might be 1, but we don't know that. So we'll just leave it as general as this at the moment. So this is all we know about A, B, and D. D is the highest common factor of A and B. A and B are integers. They're not both 0, because we need a highest common factor to make sense. Now, the next thing that's going to stay the same in the whole of the workshop is we're going to take a set. This set involves, well, here's a notation for it. It's all things you can get of the form m times a plus n times b, where m and n vary through the integers. So a and b are constant in this whole session. M and n are dummy variables here. It really doesn't matter what m and n are, okay? You could use other letters. But you mustn't use a, b, or d because they're in use. A, b, and d are fixed in this session. You don't have to use m and n. They're the dummy variables. We look at every possible integer multiplied by a and add it to every possible integer multiplied by b. Maybe that's a bit abstract, so let me just point out a few things that are definitely in there. For example, remember, a and b, we don't know what they are, but they're constant in this session. 3a plus 7b is going to be in S, because you can take m equals 3 and n equals 7, and that will give you one of the things in S. You could take m equal minus 2 and n equal 1, and that will give you minus 2a plus b. Or you could take m equals 10 to the 9 and n equals minus 10 to the 8, and that will give you 10 to the 9a minus 10 to the 8b. It doesn't matter. Why does it say positive integers? That is wrong. That must have been there forever. Whatever pair of integers, get rid of that positive. It shouldn't be there. That's been there for 3 years, and nobody's ever pointed it out. Okay. It wasn't false. It's true that whatever pair of positive integers you chose, the combination would be in S, but you could also use negative integers. So scrub out that word positive, and I'll try and make sure it's gone by next year. Right. Now, don't forget, D is still the highest common factor of A and B, and those three things don't change at any point in this workshop. We don't know what they are, but we do know that D is supposed to be the highest common factor of A and B. And we want to prove Bézout's lemma, which says that there's at least one pair of integers, m and n, so that when you combine m times a, do m times a plus n times b, which I think of as combining a multiple of a with a multiple of b, using m and n as your multiples, and then adding them together, there's at least one way to do it so you get D. Now that's another way of saying that D is in that set, because S is the set of everything you can get of the form ma plus mb. So all we're saying here is that D is supposed to be in that set S we had before. What was S? S is a set of everything you can get in the form ma plus mb, where m and n are integers. And Bézout's lemma is saying that D is in this set. There is a pair of integers m and n that work so that ma plus mb gives you D. actually we're going to prove more. We're going to prove that D is actually to the minimum positive element of that set S. We first start with something easy, because let's check there's at least some positive elements in S. Okay? Otherwise, it wouldn't make sense to talk about the minimum positive element of S if there weren't any positive ones. And when I say positive, I mean strictly positive, because 0 is boring, right? You can always get 0 by doing 0 times A plus 0 times B. And that's in S. 0 times A plus 0 times B is 0. That's in S. But it's not very exciting. So when I say the minimum positive element, I mean it's the next one up. The next one above 0 is something in S, assuming there's something positive in S at all, which we're going to prove. And we're going to prove later that it's actually equal to D, the highest common factor of A and B. And we're going to work our way through with some easier stuff first. Right, so your first choice is to try some particular values for M and N, which could be 0 or plus or minus 1 or things like that, to show that A, minus A, B and minus B are definitely in S. And having done that, that should be enough to convince you that at least one of the things in S is positive. We don't know whether A or B are positive or not, but at least one of A and B is not 0. And if A is not 0, then A is either positive or negative. And then you can try case-by-case analysis. Okay, so there's only about 4 cases to deal with. And then you'll know that S has got at least one positive element. Okay, so we'll come round and see if you're getting on okay with that. I shall pause the recording and we'll come round and see. Okay, I'm going to give you my version of this, but I mean there's plenty of ways to express it. I haven't even decided what I'm going to write yet, but we'll have. Okay, so M equals 1, N equals 0 gives A equals 1 times A plus 0 times B is in S. And similarly, B equals 0 times A plus 1 times B is in S. That's M equals 0 and N equals 1. Minus A is minus 1 times A plus 0 times B is in S. And that's all. This is all very boring, right? But if somebody asked you to really say what combinations would you use, these are probably the obvious ones. 0 times A plus minus 1 times B. Okay, now I've decided to do this differently from the way I normally do it. Note that mod A plus mod B is greater than 0. I normally do mod A or mod B, but mod A plus mod B is greater than 0. This is a bit. I'm cheating really. I should be deducing it by looking at 4 possibilities. But let's do it slightly differently. Mod A plus mod B is greater than 0 because A and B are not both 0. At least one of A and B is not 0. And mod A plus mod B is, well, it's plus or minus A plus or minus B, but I don't mean that they have to be the same sign, right? And that's going to be in S as well. But the alternative is you say at least one of A and B is not 0. If A is not 0, then at least one of A and minus A is positive. If B is not 0, then at least one of B and minus B is positive. So at least one of these 4 numbers is positive, strictly positive, and it's in S. Any questions about question 1? Okay. let's move on to question 2. Now we'll assume that x and y are in S. Now I told you that m and n were dummy variables and you could use any letters. That's rather important here. X and y are in S. Each of x and y has its own pair of integers. But you can't call them m and n for x and call them m and n for y because they're probably a different pair of integers. Okay? So you need some notation. You could use x is m1a plus n1b and y is m2a plus n2b, or anything that shows that you realize that they're probably different combinations of a and b. But you use the fact that they're in S, and then you take k and z, and you've got to show that x plus ky is in S. And really, once you've done that, there's no real difference about x minus ky, because minus k is an integer anyway. So if x plus ky is in S for all integers k, then minus k is just another integer, like k is. So you only really have to prove one of these. Okay? But it is, we'll use the x minus ky later, so you might want, it doesn't really matter which one you do, but you might want to remember that one. Okay, let's see how you get on with this one. And the notation is the only problem here. We'll come round and see how you're getting on. Okay, so I've started the recording again just so that I'll show you my version of this. There's lots of different notation you could choose. I suggested one with the M1s and the M2s and so on. So since x is in S, if you get up quiet please for my version of the proof. Since x is in S, there are m1 and n1 integers with x equals m1a plus n1b. Similarly, since y is in S, there are m2, n2 in Z with y equals m2a plus n2b. Then x plus ky is equal to m1a plus n1b plus k times m2a plus n2b, which you regroup as a multiple of a plus a multiple of b. So it's m1 plus k m2 times a plus n1 plus k n2 times b, which is in S because m1 plus km2 and n1 plus kn2 are integers. Okay? So we've got it in the form integer multiple of a plus integer multiple of b, and they're all in S, so x plus ky is in S. So you can do nice things inside S. In particular, k equals 1 means you can add two things in S and you get another thing in S. But you can add any multiple of anything in S, you get another. X minus ky is the same. You can deduce it anyway. So let me just say x minus ky is similar. So actually, you could just use the integer minus k. But you might write it out just for practice. Okay, so right, so that does that one. Any questions about that? Okay, so we're making some progress towards Bézout's lemma. We've proved some easy facts about S. S is quite a nice set. It's got 0 in. It's got at least one positive thing in. If you've got two things in it, you can combine them in nice ways like this to get other things that are in it. Okay, so S is a nice set. You'll find out more about what sort of a thing S is when you do mathematical structures. It is a subgroup of the integers, and subgroups of the integers are, under addition, are very special. So you find out more about that. Okay, so now, proves that every element of S is divisible by D. I tell you what, I'm going to just do that one for you because I think that one's, I sort of did it in lectures already. So I'll just remind you why that one's true. So let X be an S, then there are M and N in Z with X equals MA plus NB. Notice, if you have to prove something about every element of S, the start of a prove something's true for every almost always starts with a let X be an S. The reason you might think, why have I taken just one thing in S when I'm supposed to prove something about every element of S? But the point is that what this means is I'm only going to assume that X is in S, and I'm going to show that from that it follows that X is divisible by D. If I only assume that X is in S, and I can then prove that X is divisible by D, then my proof shows that everything in S is divisible by D, because I only use the information that you're in S to show that you're divisible by D. And that's why we start with let X be an S. That's a typical start to a proof that every element of S is divisible by D. Okay? So then to the pair of integers with X equals MA plus MB, that's what S meant. And then, or another then, never mind, X over D, I divide X by D, that's equal to MA plus NB over D is equal to M times A over D plus N times B over D. And this is in Z. Why is that in Z? If you wanted to say more here, you see D divides A. That's because A over D and B over D are integers. Why is that? That's because D is the highest common factor of A and B, and in particular, D is a common factor of A and B. So D is a very special common factor of A and B, but in particular, A is divisible by D and B is divisible by D. So that's where these come from. And then if you combine integers like this, integer times integer plus integer times integer, that gives you another integer. So we've shown that X over D is an integer, so D divides X. So if you wanted to say that, we could put a comment in there, we know D divides A and D divides B. And the conclusion then is that D divides X. Any questions about that proof? We did it in lectures as well. Right, so that means you can move on to question 4. Now, question 4 is getting more interesting. So we take a y in S with y greater than 0. We know there are some. So now we don't know what y is yet, okay? But y is just something in S with y greater than 0. And I'm asking you to prove this rather strange-looking statement, that y is equal to D if and only if y is a common factor of A and B. Remember, A, B, and D are fixed in this whole session. So A, B, and D are not varying, but we don't know what y is yet, so y can be various different things. Okay? But A and B are what they were before. D is the highest common factor of A and B. So that's still true. And the statement here is y equals D if and only if y is a common factor of A and B. Okay? It's a two-way implication, and one direction is trivial, and the other one is slightly less trivial. So you need to try and prove two different things. One is that if y is equal to d, then y is a common factor of a and b, and that's trivial, so I'll give you that one. D is a common factor of a and b because d is the highest common factor of a and b. If you're the highest common factor, then you're a common factor. And if y equals d, then d being this thing means that y is this thing as well. Okay, so that's just a trivial substitution, right? It's the other way around that's more interesting. Suppose y is in S, and y is greater than naught, that's given, and that y is a common factor of a and b, then your task is to prove that y is equal to d. Now, that's not obvious, okay? So in other words, we know that the things in S are divisible by D. Now we're trying to show that if y in S is a common factor of a and b, then y has to be d and nothing else. But this is only true because y is positive, because if d is in, then minus d will be in as well. And of course, minus d is also a common factor of a and b, but if you allow negative factors. So the hint is to note that because y is in S, we know that y is divisible by d. And because y is greater than naught, that will give you d less than equal to y. So now, just think about it for a bit and see if you can convince yourself about all these bits. Okay, so we're going to come round and see if you manage to convince yourself of the remaining details. Okay? And then after that, we should be able to finish the proof of Bézout's lemma. But let's see what you make of this one first. So we'll come around and see if you can... Okay, I think at this point what I'm going to do is I'm going to do the rest, question 4 and question 5 for you. Some of you have actually already thought about question 5 and made progress on it, so and some of you even finished question 5. So I think what I'll do is I'll just do the rest. So we'll start with a few final details here. So what did I say? If y equals d, then y is a common factor of a and b because d is. So that's easy. So now, the next one, 2, given y is in S, y is greater than naught, suppose that y is a common factor of a and b. Now, we got this comment here, that if y is greater than naught, since y is greater than naught, we must have d less than root of y, because d divides y. So let's have a look at that. That was a previous question, that was question 3. So y over d is an integer, but they're both positive, right? Of course, if y was negative, then you wouldn't get much out of this, but y is greater than naught, and d is greater than naught, of course. Highest common factor is positive as well. So in fact, y over d is a natural number. Oops, where does that go? But y greater than 0 and d greater than 0, so y over d is actually a natural number. I'm really going around the houses. What I'm trying to say is y over d is greater than 1. This is all a bit of extra detail. It was pretty obvious, really, that this gives d less root of y, or y greater than d. Okay, all I've done there is prove that if you've got two positive integers and one's divisible by the other, then the one that's divisible by the other is at least as big as the other. So that's pretty obvious anyway, and I wouldn't take much away if you just said that was obvious. Right, what about the other bit, though? So that was the part of the hint. The other bit, now we use the highest common factor. Also, d is the highest common factor of a and b, and y is a common factor of a and b, so y is less than equal to d. Okay, we've got y greater than equal to d, we've got y less than equal to d, so the y equals d. So if you manage to find any common divisor of a and b in S that's positive, then it's D. But we haven't yet shown there is one. So the last part is to prove that the last bit involves proving that the minimum positive element of S is a common divisor of A and B, and that will finish the whole thing. We need this quotient to remainder, which we mentioned several times. This is, as before, you take an integer and a positive integer, and you want to divide the integer by the positive integer and get a quotient of the remainder. So this is x over y is equal to q plus r over y. This q is an integer, and the r over y is a genuine fraction, a proper fraction. R is greater or equal to 0 and strictly less than y. So we've got it into the most sensible possible form, except the q might be negative. Okay. And in this setting, y divides x if r is 0, because this r over y is going to mess you up otherwise. When you do x divided by y, you get this integer bit plus this remainder over y. Remainder divided by y is only an integer if r is 0, and only if. So that's the setting we're in. Okay, so now we let y be the minimum positive element of S, and we want to try and prove it's D. But notice that y is in S, y is greater than 0, and if r is in S, implies it's not true that 0 is strictly less than r is strictly less than y. You see, y is the minimum positive element of S. Okay? So yes, y is in S. Yes, y is greater than 0, but it's the minimum positive element of S, so there's nothing between 0 and y in S. So any r in S can't be strictly between 0 and y. And that gives you this hint. So if 0 is less than r is less than y, and r is in S, well, we've eliminated 0 strictly less than r, strictly less than y. So the only possibility is R is naught. There we go. And now we're going to use that with quotient and remainder, together with everything else we've done. So, recall that A is an element of S. We know that. A is still the same A as before, but it is an element of S. We showed that earlier. Use quotient to remainder. A is equal to QY plus R for some Q in Z and R in 0, 1 up to Y minus 1. Okay? That's one of these 0 less equal to R less than Y's. R should be an integer here. Well, it says R was in S, so that follows. Okay. But then R is equal to A minus QY. Y is in S, A is in S, Q is an integer, and we showed earlier you can combine things in S to get things in S. Can't remember whether that's question 2 or question 3. I think it was question 2. So A was in S, Y was in S, Q is an integer. Q is playing the role of the K earlier. A is playing the role of the X earlier. So this is like an X minus KY, which is still in S, because X and Y were in S, and Q is an integer. Okay? So now R's in S. R is one of these numbers, 0, 1 up to Y minus 1. So we're in this setting. R's in S, and 0 less to R less than Y. So R must be 0, because R can't be strictly between 0 and Y. We know that Y is the minimum positive member in S. So R is 0, but if R is 0, then A is Q times Y. A is divisible by that. But it's completely symmetrical between A and B. You just do the same argument, shows that Y divides B. Shows that Y divides B, not A divides B. So now Y is greater than 0, and Y is a common factor of A and B. So by question 4, Y equals D. Anything in S that's a common factor of A and B and is positive is equal to D. So Y equals D. If you go right back to the beginning, Y is the minimum positive element of S, and now we've shown that Y equals D. Conclusion, thus D equals Y is the minimum positive element in S. And we've finished. Okay, now that was a bit more complicated. Any questions about that? If not, stop there and see you on Monday.